7.3 voltage and sources of potential energy. So remember before I said the voltage is the amount of energy that's being given to the electrons. So if we have a look here, they've got an analogy here between gravitational potential energy. So when you lift something up, you're giving it energy, and then when you let it go, it loses that energy. So you can read through that and see whether that helps make sense for you. The meat here is this bit here. Work, which is the amount of energy it takes to do something, is equal to the size of the charge, the electric field strength, and the distance that you're moving that charge. Don't use this formula very much. It's just a lead into some of this other stuff. It says if we do 1 joule of work on 1 coulomb of charge, so work and energy are interchangeable. It's measured in joules, the same as energy is. 1 joule of work on 1 coulomb of charge, then that means you've increased the potential, the electric potential, so the potential energy, by 1 volt. Now, it's annoying. They use electric potential, voltage, potential difference, and there's yet another one, EMF. As far as I can tell, they're all exactly the same thing. So why someone didn't put their foot down and say, we're just going to call it this, I do not know. So electric potential energy, what does he say? We can also have increase the charge's electric potential energy by 1 joule. So electric potential is measured in volts. It's the same as voltage. So 1 joule of work on 1 coulomb of charge produces an increase in electric potential, because it's potential energy, it's stored up energy, of 1 volt. So then there's an example. It took 10 joules of work to shift a 2 coulomb charge from A to B. Notice they're not worrying about this distance business. This was just an introduction. We would say its electric potential has changed by 10 joules. So that's 5 joules for each coulomb. So the electric potential, work divided by charge. Electric potential is a scalar quantity measured in joules per coulomb, whereas this gravity thing falls through here because it's not per kilo. This is per coulomb though. So this is an important one. Electric potential, voltage, is the amount of work done divided by the charge. So it's the amount of energy that's been given divided by the size of the charge. So 1 volt is 1 joule per coulomb. That -1 means per, so it's joules divided by coulombs. Right. Potential difference is the difference in electric potentials between 2 points in an electric field. So they've got some charge being moved from A to B, and there's a difference in the voltage between the two. So potential difference is much the same as voltage. It's measured in V in volts. I guess it's a change in voltage, but you won't see it anywhere with that little delta sign. They just drop it and use V. So it says here, instead of delta V, we can just use V for potential difference. Excuse me. And then it talks about batteries and how they work, and the potential difference is measured in volts and is usually referred to as the electromotive force, EMF, just to confuse you a little bit more. EMF is when they're talking about a cell. A cell is just like a single battery. The word battery actually comes from a lineup of things. like in a row. So you can have a battery of cannons at a fort, or a battery of, I don't know, usually they talk about it in terms of rifles and cannons and whatever, where they have them all lined up in a row. And in an actual battery, that's what it is. It's a group of cells. So, and that's why it's drawn like this as well. So this represents a cell, a chemical cell that produces electricity, direct current electricity. And you put them together like that in a series, that makes a battery. If each of these is 1.5 volts, and you put 4 of them in, then you're going to get 6 volts all told. They just add together in series. You could join your cells, so this little individual one, in parallel. I do not know what the use of joining them in parallel is. I have not seen a single example of how to use that. So they're usually joined in series, and that's how we draw a battery. A battery is a series of cells joined together, and their voltages add, and that's why you would put them together in series, to add the voltages. Alright, this diagram down here is really quite an important one to understand. So we've got the potential here. So let's start at the battery. I don't know why he didn't start at the battery. That looks like a sensible place to start to me. Right, so again, this is marked with conventional current, the way that a positive charge would move around the circuit. We've got the battery. The battery's job is to increase the potential, increase the energy of the electrons. So here's the energy increasing here while it's in the battery. As the charge moves along the wires, these are metal wires, their resistance is really low. It doesn't really take any energy for the electrons to go along there, so the energy stays the same. And you get this load element. That's something like a light bulb or a doorbell or an appliance or a motor, something that's going to use up the energy that's being supplied. And the energy drops down as it goes through that load element. And it's important to realize that the rise and the drop are the same. So if we've added, as this says, 6 volts of energy here, so 6 volts, we've added 6 volts of energy, potential energy, it will lose 6 volts of potential energy here. So when you're doing your circuit diagrams and circuits later on, you're trying to work things out, this voltage that's given by the battery is lost completely by whatever elements are in the circuit. So if there were more elements in here, then it would drop a bit, go on, drop a bit, go on, but it would end back up at 0 before it gets back here to the battery. And it takes, in these connecting wires, we say that it doesn't lose any energy at all, because they're metal, the resistance is really low, and the lengths are quite small in a circuit like this. So it's not going to lose any energy, measurable energy going through the wires. Then we've just got how you connect a voltmeter. So this is our element, that's a light bulb. We've got a cell here, we've got a light bulb, we've got a switch, and the voltmeter is connected, we say, across the element that we want to measure the voltage drop in. So in this diagram, they've gone right here to the corners, but you could have just gone like this and just put it, as long as it joins on each side of the element, right, for a voltmeter, because a voltmeter measures the change in energy across an element. So measuring from here to get the voltage drop as it goes through there, or you could measure from there to there to get the voltage increase, the energy increase as it, potential energy as it comes in through this battery here. Measured in volts, you can analog ones, or you can multimeter it.